But the tricky way of solving linear systems involves using matrices. And so while we're going to go through this exercise of very quickly and easily solving big linear systems using matrices, we might as well learn a thing or two about matrices, at least how to manipulate matrices on a calculator. So that's kind of, it's only going to be, probably like a week, and we'll be done with this. So it's very quick. It's only going to be one test. A graphic calculator test is the only test we'll have. What about this stuff, though? So what are matrices? Okay, matrices are things like this. I'm just going to draw one. This is a matrix. That's a matrix. A matrix is just a collection. Let's have everybody turn physically completely around so you can see it. So it's going to have to be plugged into this. Okay, matrix is literally just a collection of numbers. Well, that allows, and the nice thing about matrices is you can use matrices in many cases in the same way you can use numbers. But it's like having, instead of just having something like 2x plus 3 equals 9, it's like having that 2 explode into a bunch of extra information. All the parts of this would, instead of being just wimpy little numbers, would be matrices, where there's a lot more included. Matrices could be as big as you want, too. You could have a matrix that's 100 by 150.
What about infinity?
You want to say it again?
What about infinity?
Well, I don't know. In theory, I suppose, but that's anyway. So that's what a matrix is. Today I want to just do a couple things. I want to just teach you what the anatomy of a matrix is. What is it? How do we describe them? How do we do some simple arithmetic with matrices, adding, subtracting, multiplying? And then I'm going to hopefully at the end just give you a brief glimpse of how can you use these weird creatures to solve linear systems easily. And keep in mind, you might think, well, why? I don't know how to solve linear systems. Well, sure, but the linear systems that you guys have solved so far have been really wimpy. They've been 2 by 2 linear systems, meaning 2 variables, 2 equations. Now, they're useful, and I don't want to diminish what you've done. It's good stuff. But bigger linear systems are harder to solve. For example, look at the 2 methods that we've used to solve linear systems. Okay, we had a graphical approach where we just graphed the lines and found the intersection of the lines, right? And then we had an algebraic approach where we used either substitution or linear combination. So what about those? Could we use those for bigger systems? Well, yes and no. First of all, if we wanted to, for example, look at a 3 by 3 linear system, and what would that even look like? So here's an example. Here's an example of a problem, hopefully at the end, that we will
Are you recording?
do. Yep, I'm recording.
Okay.
You got it. Well, good thing you're checking. You got to check up on me and stuff like that. So here's an example of a 3 by 3 linear system. You can see that. I'll make it a little bigger. Okay, what's that mean? Okay, it just means that now, instead of 2 variables, we've got 3 variables. So the first linear equation is x plus 5y minus 3z equals 11. Okay, why is that a linear equation? Well, it's a linear equation because all of the variables are to the first power, the x and the y and the z, and they're all just multiplied by constants. Okay? So what does it look like? Now, the linear equations that we have dealt with in the past we've been able to graph them on the xy plane. Okay, that's not the case this time, though. This time, let's do that. For example, we were able to do stuff like this, right? If we had 2 lines, we could just graph those 2 linear equations, and that's the solution right there, the point of intersection. Okay? Because if we have a 2 by 2 linear system, x's and y's, the equation of a linear equation involving 2 variables, x's and y's, always looks like a line, doesn't it? These don't look like lines. These are different. Now we've introduced z's into the mix. And if this is the x-axis and that's the y-axis, remember from one of our previous discussions, yeah, the z comes out of the board. And so now all of a sudden we're talking about three-dimensional space instead of two-dimensional space. And the equation of a linear equation in three variables looks like, here's a back table. In three dimensions, a linear equation looks like a plane, like a flat plane floating in space, and not a line embedded in a plane. And so when we look at the intersection, and we've talked a little bit about this, when we look at the intersection of a 3x3 linear system, then we're looking at three planes that are, that are intersecting maybe at a point. Okay? If there's a single solution, it's at a point. You can't graph that on your calculator, can you? You can't graph planes in three dimensions. It's two-dimensional. So we're stuck. Not yet, exactly. So we're stuck. And if you went beyond that, if you went to like four-dimensional systems, you can't graph them at all because you can't graph things four-dimensionally. Our universe only permits us to visualize three dimensions, right? And so, it's, I suppose maybe there are universes where four-dimensional or five-dimensional teachers could be drawing on a four-dimensional board, and they could somehow be, we can't imagine what that would look like. And then, well, okay, in our universe, we'd say the fourth dimension is time, but it could be that there are other universes with more than three spatial dimensions, and then maybe they could do these tricks, but we can't. In a four-dimensional universe, I mean, just to give you an example of how weird that would be, in a three-dimensional universe, my shadow has how many dimensions? Look on the board. I could make little animals up here. But it's two-dimensional, isn't it, right? A shadow on a flat surface is two-dimensional. Now, in a four-dimensional universe, I would be casting three-dimensional holographic shadows on a volume. It'd be really strange. So, yeah, you can get an idea that it gets a little strange. But we don't need to go there for now. Hopefully, my goal is, by the way, we can do this one quickly enough, then prior to the vacation, maybe we can take a day or two and just talk about dimensionality.
Yeah.
Okay, so there's your motivation. All right, so, but anyway, so we already kind of shot down the graphical approach. The calculators, we can't find solutions to bigger linear systems by crossing lines anymore, unfortunately. What about algebraically? Well, yeah, you can solve large linear systems algebraically. In fact, I've contemplated having you guys solve 3x3 linear systems algebraically, and I just feel like there's not enough time to do that right now. Maybe we'll come back later and do it. It's not a big deal. It's really not a big deal. There's some value to it, but honestly, people that solve linear systems in the real world do it the way with the trick I'm about to show you, with the by using matrices. And so it's of limited practical value to do that anyway. We may come back and do that later. But when you get into really big systems, it gets very, very complicated. Like if we were to do a 12 by 12 linear system, 12 variables, 12 equations, man, that would take a really, really good college math student hours or days to do. It would be a ridiculous amount of time. So it's not something, well, and it may have a purpose. There may be, there really are reasons that there may be a 12 by 12 linear system that you need to solve for some variables when you're making a weather model or something. But we wouldn't do that manually, because you can do that. You guys will be able to do that on your calculators as quickly as you can type in the information into a 12 by 13 matrix and push go. Your calculator will do that for you that easily. So you can solve arbitrarily large linear systems, meaning as big as you want, with, at some point you'd probably fry your calculator. Not fry it literally, but it'd start to run out of memory and wouldn't be able to execute that large calculation, but computers can do it easily. A computer could easily do a 12 by 12. In fact, a computer could probably there are probably computers out there that can do a 10,000 by 10,000 linear system that would, they're big computers. But they're out there. And so technology allows us to do these matrix row operations very quickly, solve linear systems, piece of cake. Okay, so that's really where we're going with this stuff. Okay, now, to get there. Brief introduction. So matrices. Okay, so this is an example of sort of a representation of a matrix. This one looks kind of strange, though, because normally instead of these A's, we're going to have just numbers in there. So this would be like a 1, and that would be an 11, and that would be a negative 113, and that's a 0, et cetera, et cetera. This is just meant to show you kind of what matrices look like. So we always break matrices up into, they're a regular arrangement of numbers broken up into horizontal rows and vertical columns. Okay? And all these these little A's and these numbers on here represent are just the positions of those entries in the big matrix. So if this is row 3 and this is column 2, then where row 3 and column 2 collide, which is right there, we get entry we call A sub 3, 2. Right? Row 3, column 2. That's going to be a number for you guys then, okay? So this is just sort of a generic template for what all matrices would look like. Here's a specific matrix. Oops, let's talk about dimensions first. So the dimensions of a matrix are always written in the order the number of rows first and then the number of columns. So for example, what are the dimensions of that matrix? We call it a 2 by 3. There's 2 rows and 3 columns, and that's how we write the dimensions of that matrix. Okay? What is this one? 3 by 3. Sure. Okay? What that one? 2 by 1. Good. I get 2 very small rows, but they're there, and 1 column. Right? It's 2 by 1. 1 by 2. Okay. 1 by 1. Yeah. Okay. All right. So so that's what matrices are. What they represent could be lots of things. You know, I'll maybe talk about that more a little later. But for now, how do we do stuff with them? How do we do arithmetic with them? Because they're sort of like numbers. They're just like complicated, multi-dimensional numbers. So to add or subtract matrices, they have to have the same dimensions because the way we do it is just by adding or subtracting corresponding entries. So for example, if I want to add matrix A to matrix B, I'm just going to add the row 1, column 1 entry of matrix A to the row 1, column 1 entry of matrix B. So -5 plus 6, 0 plus -3, 4 plus, yeah, you got it. So it just looks like that. That's my answer. Okay, no big deal, right? If I want to subtract matrices manually, we do the same thing, only we subtract, right? Corresponding parts get subtracted. So we get 1 minus 1, 2 minus negative, etc. Looks like that. And there's our answer. Okay? Now you can see how it wouldn't work to do something like this, right? What if I wanted to do this? What if I wanted to do that? Doesn't work, does it? It doesn't work. They don't match up. These two go together, these two go together, but there's nobody to go with that 7, so it doesn't work. Okay? Make sense? And your calculator would tell you that. If you tried to do this on the calculator, as I will show you in a second, your calculator would say error dimension mismatch, meaning the dimensions of the matrices don't go together for addition. Okay, so let's actually do this on the calculator. Let me show you how this is very simple. This is one it wouldn't even be worth putting this into the calculator, honestly. This one's easier just to do manually. But later on, they'll be hard enough that you won't want to do them manually. Okay, so how do you do this stuff? Okay, notice that on the calculator, matrices get their own button and their own screen. So if I hit second and then I go down, see this button right here where it's got a matrix kind of behind? Second matrix, it takes me to that screen, the matrix screen. Okay? How do you delete matrices? I don't know. If I hit clear, does that do anything? No, it doesn't do anything. I'm not even sure. I think maybe, I've never really tried to do this. You don't have to. And I bet if I go variables, is there a, I don't even know.
It says clear entries.
Where does it say? Clear all entries, let's try that. Okay. Let's just see if it did it. It honestly doesn't matter. Nope, didn't do it. Maybe it's variables. I don't know. You could reset the whole thing.
Hit 4. You can hit 4.
Sure, string, table, I don't know.
Oh, yeah. Are you trying to like reset the table?
No, I was trying to clear the matrices. I don't know how to do it.
What you do is go to separate,
Mhm,
and then push the matrix in,
mhm.
over to edit, and then you press enter. And then
Okay, but then how would I just clear that one out?
you have to fix it first before you can clear it. You can put in a number.
Really?
I think so.
Or if you
Oh.
go to the second memory
And which one's that? Okay,
second, the plus button.
okay. I wonder if I just did 0 times 0, if that would clear it. Oh, I don't know. Let's try that. Not, and I'm just wasting time, 'cause it doesn't matter. Clear all lists. Doesn't matter. Good question. Okay, yeah. Anyway, I've never even tried that before. You're the first time I've ever even looked for it. Because you never ever need it. Anytime you need to do a matrix, you're just gonna create the one that you want anyway. And if there was already one in there that's A and you wanna make a different one, just make a different one. So like in this case, now if we wanna add these two up, we're just gonna make the first one, typically the first one will be matrix A. The second one will be matrix B, and we'll just build those matrices on our calculator, and then ask our calculator to add them up. So to do that, now what are these menus? The first menu, the names menu, is the one that you use the most. That's the one where you go to actually grab a matrix to do something with it. Okay? We have to build the matrix first, though. To build the matrix, we're going to skip over to the edit menu. So hit the left arrow once, and it gets you to the edit menu. And then we just choose the number corresponding to the matrix that we want to build or change. So 1 for A. Now right now, the current matrix A is a 3 by 4. What should ours be? 2 by 2. So we just go, now here's, this might seem kind of trivial, but this really does make a difference when you're building big matrices. You want to use the enter button instead of using the arrows. So we just go 2, enter. Notice it builds 2 rows. 2, enter, builds 2 columns. And then we're just going to enter the matrix, the numbers in the matrix, just like we'd read a book. So left or right across the page and then down. So we would just go 4, enter, -1, enter, 6, enter, -3, enter, and it'll populate that matrix in that order. Okay? So there's 1. Now when I'm done with the matrix, I have to quit. I go second quit to get out of there. I'll just clear all that stuff off. And then I'll go second matrix, edit 2 to build matrix B, which also needs to be a 2 by 2, which it already is. So I can skip down to the first one. I guess I have it in there already from last class. So -6, -5, 7, 3, right? Okay. Once you get that in there, just quit. And then all we have to do now on our home screen is just do matrix A plus matrix B. So I go second matrix A, so just 1 for A, plus second matrix 2 for B, hit enter, there's the answer. How about that? Okay, for matrix addition and subtraction, that's a pretty easy thing to do. I mean, you don't really even need to hardly use the calculator for that. But as we're going to see with matrix multiplication, it's a whole different story. Matrix multiplication is much more involved manually than addition and subtraction. Okay, so moving on. Okay, so we could also, we can do subtraction the same way. Okay, scalar multiplication. What does the word scalar mean? I'm just going to give you a brief introduction to a couple science words that pop up in math a lot. Scalar and vector. Some of you may have already heard of these things a little bit. You've probably had some limited exposure. Scalar quantities as opposed to vector quantities. Scalar quantities are things that can be completely understood or communicated with just a single number. So for example, what page are you on in that book? Is a scalar quantity. If you're on page, 173, then that's all it takes, 173. What's the temperature of the room? 72 degrees. That's a scalar. But certain quantities don't just need numbers. If I wanted to, for example, describe a force, let's say that I wanted to kick a football through the uprights in that direction. What do I have to do to the football to make it go through the uprights? Okay, but when I'm kicking it, what am I exerting on the football? Okay, a force, right? I'm going to exert a force on the football to cause it to accelerate up into the air and go. Okay, but if you just say, okay, well, kick it with 200 pounds force. Okay, I'll kick it in that direction. That's not good. The uprights are over there. I need more than just the amount of force that needs to be applied to the football. I also have to explicitly give a direction. I need to point in the direction that that force needs to be applied. Force is therefore a vector quantity. The number is not enough. We need both a number and a direction. Okay? So why do I bring this up? Well, because that's one of the things that matrices are really good at, is doing arithmetic involving scalar quantities and vector quantities. Vectors can be represented by matrices. Okay? Scalars are represented just by numbers. So what happens if I want to multiply a scalar, k is just some number, let's say, times a much more complicated thing, a matrix? What do you suppose I do? What do you think? I think I heard it. On the calculator, that's all I do. What does this mean, though? If I multiply k times this matrix, what's the result going to be? What do you think? I just distribute it all the way through. That's it. Okay? Very simple. So, for example, what do I get here? This is another one. You don't even really need a calculator for this. If I do 3 times this matrix, in order, what are the entries going to be? Negative 9.
0, 12, 15.
Yeah, that's it, right? No big deal. On your calculator, all you do, very, very simple, just like you'd expect, if I want to multiply, it's not good. If I want to multiply like the matrix A that we already built times 10, I just do 10 times matrix A, and I get that. No big deal, right? Just like you'd expect. Okay, so far so good, pretty easy stuff. Same thing here, I just multiply the 5 all the way through, and I could even have variables in the matrix. Yes, ma'am. Yes, you may. Okay, but how do you multiply matrices? Well, before we get into that, I need to tell you something about matrix multiplication. We said that matrices act like numbers. For addition and subtraction, they act exactly like numbers. If I have 3 matrices that are being added, just like with numbers, it doesn't matter the order in which I add those matrices up. It makes no difference. If I'm adding 2 matrices up, I can commute them. So matrix A plus matrix B is the same thing as matrix B plus matrix A. It makes sense. All I'm doing is combining the like entries anyway, right? The corresponding entries. So what difference does it make the order in which I'm adding those numbers? But it gets a little more complicated when you introduce multiplication. So for example, if I'm multiplying matrix S times the quantity matrix A plus matrix B, this is where it starts to get a little bizarre. If I'm distributing the S from the left, then the S has to appear on the left side of each of the matrices after I distribute. The reason for that is because multiplication is not included in these properties. Matrices don't act like numbers when it comes to multiplication. For example, matrix multiplication is not commutative. Matrix A times matrix B, and let me say this very clearly, matrix A times matrix B is not the same as matrix B times matrix A. Just changing the order in which you multiply matrices dramatically changes the outcome. Okay? So that's where things get a little strange, is with matrix multiplication. Now, how do you multiply matrices, and when can you multiply matrices? And why is this slide so messed up? I don't know that. If we have 2 matrices, matrix A times matrix B, I can only multiply those matrices if their dimensions match up in this way. When I write the dimensions of the first matrix and the second matrix out, I can only multiply them if the inner 2 numbers are equal. Otherwise, they do not multiply. Okay, so for example, and then if it works, if the inside numbers match up, the outer two numbers end up giving me the overall dimensions of the product. So does this work? If matrix A is a 2 by 3 and matrix B is a 3 by 4, can I multiply them?
Yes.
I can. I can because the 3's match up. What are the dimensions of the product going to be? 2 by 4. Okay. Okay. Does this work? 5 by 3 times a 5 by 2. Does not work. You're right. Okay. So how do we do this? Let's try this on the calculator. Okay. Does this work, by the way? Is this one? Are these going to multiply based on their dimensions? Yeah, they do, don't they? They work. They do. What are the dimensions of the first one? A 2 by 1 times a 1 by 2. Yeah. Okay. So that works. And I'm going to get what for my result? 2 by 2. Would it work to flip those around? If I called this first one A and the second one B, could I multiply B times A? I could. In this case, I could, couldn't I? If I did B times A, I'd get a 1 by 2 times a 2 by 2. So what would the dimensions of that product be? Oops. Actually, that's not a 2 by 2. It's supposed to be a 2 by 1, isn't it?
That would be a 1 by 1.
There you go. So I get a 1 by 1. Totally different dimensions. Obviously different answers then, right? Okay. Right? Let's do this on our calculator. How do we do this? Well, it's pretty simple, just like you'd expect. Okay, so I just go into the matrix editor. Edit matrix A to be a what? If I'm going to do this product, let's say. 2 by 1. Okay, and then it's just 2, enter, -5. Okay. There's matrix A, quit. Go into the matrix editor. Matrix B is going to be a 1 by 2. And -1, 3. Okay, and so if I quit, and I do matrix A times matrix B, sure enough, I get a 2 by 2. Okay, there it is. How do we get those numbers? It's complicated. Okay. What about B times A? Matrix B times matrix A 1 by 1. How about that? Strange. Very strange.
You're never going to have to learn how it does that one.
No, you're not going to have to in here. Someday if you keep doing math, you'll have to learn how to do matrix multiplication. But I'm not going to take the time. Because the ones we're going to do are so big anyway, we're not going to want to take the time to do them. Okay? Good question. All right, so okay, so I guess I'm ready to skip up to, I think I'm done with this anyway. So what I want to show you now, I want to show you a quick example of how to solve a linear system with matrices. So let's take something like this. Okay, that's a good one, actually. We'll do that one. So everybody can see that okay? Okay, if I want to solve a linear system using matrices, here are the steps. It's really very simple. What I have to do, first of all, is I have to write the system in standard form. So what are the dimensions of that system? How many variables are there? 3. X's and Y's and Z's. Now, they may not all appear in each equation, but that's okay. How many equations are there? 3. So I have 3 equations and 3 unknowns, okay? So to write this in standard form, it just means that I have to write them in the same order, typically alphabetical order with the variables. So we're going to write the X terms first, then the Y terms, then the Z terms. That's already done, isn't it? Except when we put these into a matrix, they all have to line up. The X's have to all be in the same column, and the Y's have to be in the same column, and the Z's have to be in the same column, right? So how could I write that first equation? It's missing a Z, isn't it? Missing a Z term. So what does that mean the coefficient of Z is? 0, right. So I could write that as, right, negative, negative X, let's do it this way. Negative X plus 3Y plus 0Z equals negative 8, right? The second one's going to look like, what? 0x plus 2y plus 3z equals negative 9. And the third one, what? 5x, 0y plus 5z equals negative 10. Now, when we put these into our calculator, all we're going to do is we're going to create what's called an augmented matrix. We're just going to we're going to ignore the variables. As long as we've written it in standard form, we're just going to write the numbers, not the variables. So what are the dimensions going to be? So we'll really just focus on the red stuff. What are the dimensions going to be? Almost 3 by 4. Yeah, 3 by 4. So we're going to look like this. What's the first row going to be? Okay, negative. That's really a negative 1, isn't it? So negative 1, 3, 0, negative 8. Good. And 5, 0, 5, negative 10. Okay? There is that represents the whole linear system. And just keep in mind what that really means. This is the X column. So these are the X's, these are the Y's, those are the Z's, and those are the numbers, the constants, right? So this is negative 1x plus 3y equals negative 8, right? So put that in our calculator. Okay, so we got to call up matrix A, and what are the dimensions going to be again? 3 by 4. Matrix, edit, A, 3 by 4. Okay? Once we get those in there, I would highly recommend, you quit, right? I'd highly recommend, especially with these big ones, just calling up matrix A and hitting enter just to see if we got the right one in there. It's really easy to make a mistake. 1, 3, 0. That looks good, doesn't it? Yeah, looks good. Okay? So then all we do, once I've checked it, is we're going to go to the matrix menu. We're going to scoot over to the, matrix screen, scoot over to the math menu. So hit the right arrow to get to the math menu. And we want to skip all the way down to row, it goes row 1 through row 10, and then it goes A, B, C. We want to skip to row B. You can get there quicker by just hitting the up arrow and just moving up to row B. But you can also just type in alpha B. It goes right to it. What is that? RREF. It looks like nonsense. And what it means is reduced row echelon form. So what it's going to do is it's going to give us the answer to the system, in other words, in a matrix that looks like this, in a 3 by 4 matrix. Okay? So we choose that one. I'm going to skip. I'm just going to go alpha B to grab it. whenever your calculator pulls up a function that starts in a set of parentheses, what it's telling you to do, you gotta put something in the parentheses and close them. So what are you supposed to be putting in there? Matrix A. So reduced row echelon form for matrix A, close the parentheses, is that. Okay? What does that mean? If you look at that, now this is in the same, this is called echelon form. This is in the same matrix representation of our linear system that we started with. So the first column represents x's, y's, z's, and numbers. So what does that first row say? So 1 times x equals -1, because the zeros, 0 times y and 0 times z are just going to be 0 anyway, right? So that first row is telling us that x equals -1. What's the second row telling us? Y equals -3. Third row, how about that? That's easy, right? And it'll do that for as big a system as you want to mess with. So if we put that into Moodle then, it just wants to know what are the values of those 3 variables. Well, we got them. Just -1, -3, and -1. Check. Okay, and we got it. Okay, so now what about, though, there were some other situations that we dealt with, too, with 2x2 systems, and those could happen with 3x3 systems also. We could get answers where there are an infinite number of solutions, or answers where there are no solutions. How would we know using matrices? Now, here's, how many people have done this in chemistry? Have solved linear systems with matrices in chemistry? Okay, 2 people have. You guys did it a different way, didn't you? You probably did it using inverse matrices, A and B, and you did A inverse times B. Is that not right? Did you do it this way?
I think you're talking about physics.
Oh, maybe physics.
No, it was one.
Okay. Did it one time. Okay, you may do it more later in chemistry. I think maybe you do it more later in the year. But sometimes people are going to tell you that you want to do these, you want to solve linear systems using inverse matrices, and you don't. Here's why you don't. It's going to work just as easily either way if you get solutions to the system, if there's a single solution. But if there's no solutions or infinitely many solutions, using inverse matrices blows up, because inverse matrices are not defined in those situations. And so it just tells you, your calculator will give you some message like non-singular matrix. And so what that means is that either, it just didn't work. There's not a single solution. They're either an infinite number or none, but it doesn't specify. This method, though, tells you which one is going on, and a lot of times we need to know which one is it, no solutions or many solutions. And so let's take an example. I'll show you how to interpret this. So let me pull up another one here. Yes. Yes, you may. Okay, so let's do one of these guys. Okay, so here's another one. Real quickly, you can do this with me if you want to, or you can just watch me. But let's watch what happens with this one. This is going to be a different kind of an answer. So if we go back to second matrix, edit, matrix A, it's already a 3x4, that's good. So we'll just, why don't you read these off to me in order. So 5, 4, oh, whoops, not 0. 1, 16, -5 I heard. -16? Okay. Okay, so I got all those in there. Now watch what happens. If I go back, I'm going to quit, and I can quit. And if I go back to my last operation, was that, just by hitting second enter, it's already there. That's my answer. Okay, now interpret this one. This is weird. The top one says x plus 1/2 z equals 0, right? This one says y minus 0.375z equals 0, but the bottom one is weird. Okay, this doesn't look like the last matrix, does it? The last time we did this, remember, we just got the first square part of the matrix just looked like all ones in that diagonal row, kind of, in that diagonal, and all the rest were zeros, right? This doesn't look like that. So what that tells us is right away, this is not a single solution. If it's a single solution, it always looks like 1, 1, 1, zeros everywhere else, and then numbers in the last column, right? All you have to do, if it looks weird, is look at the bottom row. If the bottom row gives you a true statement, it means infinitely many solutions. If it gives you a false statement, it means no solutions. Well, what is that bottom row saying? No solutions. It's saying 0x plus 0y plus 0z. So in other words, 0 equals 1. 0 equals 1 is false, right? And so that's telling us no solutions. Now, if it had said instead 0, 0, 0, 0, that would have been true. That's like saying 0 equals 0, which is true always, and so that would mean infinitely many solutions. Okay? Does that make sense? Okay, but we can even do better than that. We can even do...
Amazing.
That's amazing. Yeah. Now, that's probably enough for today.
Thank
Yeah.
you.
Yeah.
Really boring day over there.
Those days